So I'm recording again. So so again, here I want you to graph using Desmos, the normal distribution curve with a mean of 12 and standard deviation 0.3. Okay? So let's just do that quickly together. The next example in the notes, I also have it as have them try, but I think we'll just do it together. So let's go back to Desmos. Here it comes. There we go. Can everyone see this? Yes, you can. So again, the mean, we want it to be 12. So we have 12. And then the standard deviation is 0.3, which you can write as 0.3. Okay. Now we want the mean is 12, so let's get the 12 here. So you could click and drag, with the mouse, or you could do this with the graph settings in the x-axis. You could change the bounds. So let's say it's mean 12. So let's say 9 to, see, I don't know, 15. There we go. So you see, this is what we get. Yeah, this is what the normal distribution curve looks like with a mean of 12 and standard deviation 0.3. That's what we get here. All right. It's just a quick example just to see if you can graph it using Desmos. That's all. I know the book tells you to graph it by hand. I guess theoretically you should do that, but I figured in this class, since we're meeting virtually, it's probably just better to graph it by Desmos. So, okay. Any questions on that? Okay. So let's do the next example. The next example in the notes is have them try. I wrote it as have them try, meaning I would let you try it. But I think it's better just for us to do it together since we have about 10 minutes of class left today. Here, let me. Okay. So I will post the notes, of course. Don't worry, and the video, of course, I'll post on YouTube. Okay. I will do that. All right. Okay, so here we're supposing that gear circumference for a manufactured bicycle part, it's normally distributed with a mean of 4 inches and the standard deviation is 0.2. I think I actually got this from the textbook. We're going to sketch this graph using Desmos, and we're going to answer these 2 questions. The z-score and all that stuff. So for the graph, this is actually the graph I got. For normal distribution, again, you just, in Desmos, you have normal dist. Then the first number is the mean. The second number is the standard deviation. So this is what we have. Okay. Good stuff. Okay. Next, for the z-score, okay, well, here it's 3 inches, right? We want to find its z-score, okay? So it's the same thing. We just use the formula, right? We subtract the mean, divide by the standard deviation. What's the mean here? 4. What's the standard deviation? 2. Okay? So for 3, we have 3 minus 4 over 0.2, which is negative 1 over 0.2, which is negative 5. Okay, I'm not sure why I have this here. That should not be there because this is less than. So this is less than 3 standard deviations. So the gear circumference is, let me just fix this quickly, is 9. There we go. Okay, sorry about that. It's not unusual. Now, why is that? Wait, no, that was right. Sorry, I thought it was 0.5. Oh my goodness. Sorry about that. I read it wrong. I thought for some reason I read this as 0.5. I'm sorry. But it is more than 3 standard deviations, right? It's negative 5. So since it's more than 3 standard deviations, that means the circumference here is unusual. In other words, the data value is unusual. Notice also z-scores don't have units here. Okay. I mean, I didn't put the units in, but it actually doesn't have units. Mostly because the numerator and denominator, wait, let me get the laser. Mostly because the numerator and denominator here, you would have inches on top and inches on the bottom, and they would cancel. All right. So again, I'm sorry about that. I don't know. For some reason, I read this as 0.5, but it's -5. And it's more than 3 standard deviations from the mean, right? More than 3 meaning it's less than -3 or greater than 3, the z-score. Okay. All right. For this one, this is 3.6, okay? The gear circumference here is 3.6. So again, we want to find the z-score. Well, we use the same formula, right? We have 3.6 minus 4 over 0.2. And what is that equal to? Well, that's negative 0.4 over 0.2. Why there's a double negative there. Cross that out. That's negative 0.4 over 0.2, which is -2. But this is actually within 3 standard deviations from the mean. So this is not unusual. So you can see that we're using the z-scores to determine if a data value is unusual or not. It's one of the things the z-scores can be used for. Okay? So this circumference, 3.6 inches, that's not unusual. The one before was unusual. So, okay. And again, here there were 2 negatives. I don't know how that happened, but I am sorry about that. Are there any questions, though? Okay, let's do another one then. So let's say here the test scores are at a 30, okay? Again, we have a test. It's normally distributed, right? The test scores, the mean we have is 17. And the standard deviation we have is 2.5. Okay? So now the question is, suppose a student scores a 5 on a test, on this test. What is the z-score? Well, again, we have the mean, right? We have the standard deviation. So let's calculate it. We just use the formula from before. We have x is 5 minus 17, the mean, over 2.5, right? Right, again, the mean, right, is 17, standard deviation is 2.5. Our x, our data value is 5, so we have 5 minus 17 over 2.5, which is -12 over 2.5, which turns out to be -4.8. And of course, this is unusual because this is smaller than -3. It's also negative, and we expect that, right? The mean is 17. The score here is 5, which is less than the mean. So we do expect this to be negative, the z-score, that is. Okay, let's do this one now. What test score will correspond to a standard score of 3? What test score corresponds to a standard score of 3? Well, so again, same idea, right? But now x is unknown, z is given, right? We want to solve for x. So what do? Right? We have this, just like before. I multiplied both sides by 2.5, as you can see, because then these are going to cancel. So we get x minus 17 on the left. On the right, we get 7.5, 2.5 times 3. And now we want x, right? We want to get x all alone. Let's add 17 to both sides, right? We add x, we add 17. X is all alone on the left. On the right, 24.5. So a score of 24.5 corresponds to a z-score of 3. And that's what we get here. Are there any questions about this example or the previous one? Okay. I put this slide here just really to remind you that one of the uses of z-scores is actually to determine what percentage of data values for a normal distribution. If you have a normal distribution, not necessarily the standard one, you know, what percentage of data values are less than this number, greater than that number, between two numbers, sort of like generalizing the empirical rule. You know, is this data value unusual, like the examples we saw? Is that data value unusual? You can do all that using z-scores. You just have to convert the data values to the z-scores. And then what you might have to do is look at the area under the graph, which is actually not easy to find. But it turns out we don't have to calculate it explicitly. It's actually given to us. What's not obvious, though, it may not be obvious at least, that that percentage we're looking for is actually the area under the graph. And this actually takes a lot of calculus, but it turns out the total area under the graph of the normal distribution curve is 1. You know, that's not obvious, I know. But don't worry, I'm not going to ask you to prove that because that requires calculus. All right, we have to stop anyway. So we'll pick up from here on Wednesday, okay? Remember, the homework is, here, let me stop this.